pretty clearly, it's not just going to be software in the cloud. It's not just going to be applications. It's going to be in things. And so I think that's really exciting. I saw that as part of the agenda, and I thought, great, okay, so let's find out about that. So we've got some great talks about that now. Our next speaker, I'm really looking forward to this. I've just found out also they're based in London, so it's going to be easy for me to meet them again after the talk and find out more. But I'd like you all to give a really warm Lisbon welcome to Ville Kuosmanen.
Right. Yeah, thank you, James. Let's definitely have a pint at some point in London when we're in there. Can I ask you, actually, how many of you are working on robotics? Are there any robotics people in the room? A few hands, not too many, but a couple of people, which is good. So this one's not going to be too much about LLMs, agents, and stuff that everyone else is talking about. We'll get a short break from that. Robotics sometimes is a bit of its own bubble, but I think over the past week we saw at least one break from robotics into the public consciousness, and that was 1X, a California-based humanoid company that announced sort of a pre-order for a home humanoid. I don't know if how many people saw the 1X announcement? Quite a few people. There was definitely a lot of hype caused by this, people saying, okay, this is finally happening, we have humanoids going into homes, the Jetsons or whatever people are saying. But there was also some criticism, I think healthy criticism to some degree, that in the videos, not everything the robot is doing is autonomous. We have sort of, a man behind the curtain or whatever, controlling the robot with teleoperation. So AI robotics maybe not quite as mature there. But this teleoperation idea that we have sort of humans controlling robots that then do tasks is seen as a bit of a dirty secret of the industry. That robot there, that's not autonomous, that's not AI, that's just the guy behind the curtain. But I actually don't think that's a productive way to look at it. I think that shared autonomy, which is this idea that we have humans and AIs collaborating to control a robot, is kind of not just a way, but almost the only way to make AI robots work in the short term, and also possibly the only way to make them work in the long term. And companies that choose to wait until sort of full autonomy, we have full-on AGI that can control robots in any condition, any environment, any task, these companies will fall behind. Bold claim. Why do I think that is the case? I think that's because robotics is becoming more of a data problem. We always speak about the data gap of robotics in almost every other modality. Think of language, speech, images, videos. We have the internet, which we can use for pre-training. That's sort of books also, movies and so on. That's hundreds of years of whole humanity's collective experience that we can basically distill down to the weights of a language model. In robotics, we don't have the internet of robotic actions to train from, which is why people are either trying to sort of cheat their way through it by maybe, let's say, taking videos of humans doing things and then saying if we have a humanoid robot, we can then transfer the human video directly to the robot. That's part of the reason why you're seeing so much action in humanoids, by the way, is because if we don't have the data for more industrial-looking arms, let's make the robot itself look like a human so we can then train it with human data. It doesn't really work, but maybe it will work more in the future. Works better today than it worked a year ago, but still, some people are also saying, okay, we can simulate the robots, we can gather as much data as possible, we just buy enough NVIDIA GPUs, and we simulate this. Unsurprisingly, NVIDIA themselves love this approach. They're saying simulation is the future. They'd love to make the GPUs for this. But the thing that's actually working is collecting data from real robots and then training models based on that. And the teleoperation approach, what I mentioned 1X are doing, is basically based on the idea that we ship the robots into real environments, doing real tasks, and we then collect this data and then train our models based on this. So kind of the more robots we ship, the more, better our models get. We grow our data sets in production rather than our competitors who don't grow them. And we also sort of gain some revenue, iterate on the product and so on. And I think that's where the idea of shared autonomy, where we automate the tasks that we want the robot to do, whether that be washing dishes and folding laundry in homes, or pick and place or assembly in factories, where we automate these tasks gradually rather than just upfront. We start from automating the easy parts of the task or motions with AI, and then train the AI to ask for help from humans on the more challenging bits or when it gets stuck. So we sort of start from 10% AI, 90% humans, until we are sort of mostly AI, but still humans able to take control when needed. So we can expand our robot fleets with a small support staff of people. So rather than just thinking of, okay, full-on autonomy, gradual autonomy. And in this world, our challenge really becomes, how do we detect when one of our humans needs to help a robot? How do we almost like route the robots between AIs and humans? And then that's the problem that I'm solving. And let's get the demo started. That's what I want to be showing to you guys. There we go. Just a moment. So yeah, this is kind of, okay, we have, let's see if we are managing to get the demo open. I'm basically trying to connect to my workstation back in London, which is running some of the AI models in here. Fantastic. Some good software from Tailscale to allow this to happen. Shout out to Tailscale. Not sponsored by them, but I would if they did. Basically, we have a bit of like a vibe-coded application in here, which is our demo for our system. Basically, on the right-hand side, in here we have various kinds of signals coming from the operation of the robot. To the left, you saw earlier, but you're going to saw in a moment, there's going to be the observations from the robot itself. And basically, this is running off of pre-recorded data, so that the data for this demo was recorded earlier in my flat, maybe like a couple of months ago. Don't ask me about why there's a big robot in my flat, by the way, and it's leaving soon when we get our office set up. But basically, I'm firstly going to show you some normal operations of robots. So I'm going to play what's happening in here, and we can view on these signals sort of how our models are going to be evaluating them. And some of these signals, by the way, are open source, including this one, which is sort of the reward signal. So once the robot starts, this is going to be like a measure of task progress between 0 and 1. When we're not doing anything, it's going to be at 0. You're going to see it move sort of upwards in this like nice, smooth, kind of dense rewards style graph. So the robot's task is to sort of pick up the ball and put it in the cardboard. And the reason why we're using this task is because every time we succeed once, we sort of reset the task automatically. So we don't need any complicated conveyors or like humans tending the robot. We can just have it do this as much as it wants, really. And yeah, that was just, I'm going to replay it again, but that was all successful rollouts. So basically our system, which is supposed to look at any potential anomalies or issues in the operations, didn't flag anything. So, all positive. This is, I get that this is kind of fake because we're just playing the same thing over and over again. It would be much more fun to do it live, so I could actually kind of fuck with it and see, see live if we're detecting any issues or not. But let me just get the next recording. So we have a short break here. Awkward silence. In terms of the AI model, by the way, we'll end up hearing a lot more about them tomorrow, I think, when a friend of mine, Dana, is giving her talk, who is much more knowledgeable on the subject. But this one was a relatively simple model called ACT, which is called action chunking with transformers, a small sort of single task transformer-based network that looks at the observations like these ones directly, doesn't do any human engineering of there's the ball, there's the tower. It just looks at the tokens going from the images directly and just predicts actions based on the original training data. Anyway, in this one, we'll see we didn't quite manage to pick it up. And what happened here is that the reward score that I mentioned to you earlier, that was like this nice linear graph here, is a lot messier because what we saw wasn't quite a success. But actually the end state and the start state look very similar. But we have built this additional check on top of this that can basically detect if the graph looks normal or not. It's sort of within normal bounds earlier, but then when the robot sort of resets itself so quickly, it kind of fails in that. So we get like a detection. And it's this is a bit of a fake task, so there's nothing wrong with just the arm retrying this for now. But if this was a real, let's say, an assembly task, or like a robot trying to empty your dishwasher, and it failed to grasp something, you would probably want to give control to a human remotely to sort of guide the robot, help it out. And every time you have one of these issues, the goal is we are teaching our models how to get out of bad states. One of the big problems with the robotic stuff is that we know how to do things when things go well, but just like with self-driving cars, when there's a car coming your way, that's not going to be in your training set many times. So you need to explicitly teach your models how to get out of bad states. They say that every 9 you add to reliability or consistency is equally hard. So it's just as hard to go to from 0 to 90% than 99.9% to 99.99%. So, and that's the sort of issues we have with physical AI a lot. So yeah, just to mention a little bit more about this, this app itself is not open source, but the 2 of these signals, the reward signal in here is, I actually have them here in my GitHub. This one is called Revact. And then the reconstruction loss in here, which we didn't see in action. But the goal with this is to basically try and see if there's anything unusual happening in the scene. So if there's a demo where I add a pineapple in here to the side, and it just makes it very hard for the robot to see what's happening. This one would be flagging at that case. That's found in my interpretability toolkit for physical AI, where you have some nice visualizations as well. This is basically a visualization of the attention patterns of the model. It's all over the place, but then once you get to picking up the cup, it sort of gets quite focused on that, and then on the coffee cup where it's supposed to be dropping it. Some cool stuff here. But yeah, sort of getting back to why this thing matters, and think about it a little bit more broadly. I think this conference, lots of people are going to be talking about AI agents. That's distracting. Lots of people are talking about AI agents in here, and the idea of agentic, fully autonomous AI that's just going to replace all the jobs. It's going to do everything that us humans could do in the past. But I think over the past few years, the story actually hasn't been so much about agentic stuff. It's been more about co-pilots and tools. I myself use Cursor all the time. Lots of people, professional developers, use GitHub Copilot, even though not many people tend to talk about it in the hype circles. The coding agents that you ping on your phone or whatever that then just send you a PR, they tend to get stuck. They tend to go on all kinds of goose chases. The truth is that the real world is just really messy, and getting to full reliability is real hard. And I think if we are asking our robots, especially where physical AI, we're still much further behind because of the data gap than people in language models and vision. If we're asking them to be fully autonomous from day one, we're asking a lot from these models. We're basically asking them to be physical AI agents that are fully autonomous, 24/7. So I think the most pragmatic way forward is to try and build this kind of shared autonomy systems where you sort of diffuse the AI over time. You build the capabilities to control your robots remotely. You start by teleoperating to gather data, and then you sort of, some things get automated, easier parts first, more challenging parts later, and then you still keep sort of monitoring just in case a robot gets stuck. So, you don't have to have a person actually in the physical room wrangle the robot back in and its environment back together. this approach has worked historically as well in self-driving cars. If you've ever taken a Waymo in San Francisco, you may have seen them get stuck. It has this like ping sound, and then there's like our team is getting back together. Our team is working to get you back running or something on the console. It happened to me a few times in San Francisco. This is what is going to be happening in robotics, I think, and I hope that we will be one of the companies powering this. That's all from my side. Thank you.